Thanks everybody for coming to my talk. So today I'm going to talk about two short-form make array, improve constant overlap zero noise RAM. So this is joint work with David Heath from UIUC. So let's get into it. So this talk and this session is about zero noise proof. So I'm the very first speaker, so I think it's my duty to introduce this very amazing primitive. So zero noise proof was introduced by Goldwasser, Mikali, and Rakov back to 1985. So in ZKP, we usually consider two parties, at least the proofer, Bob the verifier, where the proofer just want to prove some statement to the Bob. So for example, here is the public known Sudoku puzzles, where the Alice as a proofer knows the solution of these Sudoku puzzles. So by deploying the zero noise proof, the proofer and the verifier are going to talk back and forth. And finally, the verifier just output one single bit to indicate whether he believes Alice knows the solutions or not. So we usually consider three different properties in zero noise proof. The first one is called completeness. It means that if Alice knows the solution of this Sudoku puzzle, the Bob should always output true. So the second one is called the soundness. It means that if Alice is malicious, Alice does not know the solution of these Sudoku puzzles, after in the interaction, the Bob should output false with certain probability. The third one is called the zero knowledge. It basically means that after the interaction, the Bob should learn nothing beyond the fact that this statement is true. So of course, in the real world, we want to build some generic zero knowledge proof, not just Sudoku puzzles. And the very classical and popular way to doing it is let's build a zero knowledge proof for circuits. So here's a circuit with addition and multiplication gates. And essentially what the proofer wants to prove to the verifier is that she actually knows some input that can evaluate this circuit to zero. Okay, so circuit is nice, circuit is good. However, circuit cannot capture some very useful primitive efficiently. And in this talk, we're going to focus on one such a very classical one where we just want to implement the random access memory inside zero knowledge proof. So in particular, we want to build two types of gate. The first gate is called load. Essentially, you're going to take an index I and going to basically output the whatever you save at a position I. And the second gate is called the store gate. It's basically you're going to update this object memory with a new value x at the index side. Note that if you have a load after the store, you should load out whatever you store in the previous store value x. So more precisely in the paper, actually what we build is a universal versions of this load and store gate called access. Essentially, this access gate is going to take a single bit read and write as input, and based on this bit, this access will be either perform load or store. But you don't need to care about this for this talk. But zero knowledge RAM is very useful. In fact, our RAM has already been used in very recent work. Here I just want to highlight one that's going to be presented on tomorrow by Hao et al., which they show that this kind of primitive is very useful when you want to put machine learning inside zero knowledge. Good, so before we kick off, let me set up some terminologies for today's presentations. By clarify several things. The first thing I want to clarify is what do we mean by build an access gate. Essentially what I mean here is that we want to compile this access gate into just circuits with addition and multiplication gates. So therefore, we only need to focus on the completeness and the soundness. The zero knowledge basically comes for free because it's going to be taken care of by the backend zero knowledge proof protocols. And for simplicity, I'm going to assume that this circuit is defined over some large enough field F, where F, the size of field, is just some superpoly in the security parameter lambda. So the second thing I want to clarify is that how can we count the cost of our construction? Essentially because what we do is just circuit compilation, so what we're going to count is just how many number of gates we're going to use. And more importantly, we're going to focus on the non-linear gates, for example, the multiplication and the input gates, because the linear gates are almost for free in many zero knowledge proof systems. And I'm going to use this lowercase n to denote the number of slots we're going to access, basically how large the RAM is, and I'm going to use this uppercase T to denote the number of access we want to achieve. So what is our result in just one slide? So first, let's quickly recall that there's a very naive solution if you want to compile this access case by using linear scan. Essentially, for every single access, you're going to touch every single slot in this main memory, and finally, you filter out the one you want to access. However, this will result in an order t times n number of nonlinear gates. So our construction essentially achieves this with order t plus n a nonlinear gate, and also the hidden constant inside is really, really small, it's just 10. So when t is basically omega n, this means that the amortized code for each access is just small constants. Essentially, we indicate by our title, basically our construction show that to build a zero-knowledge RAM, this problem can be reduced into 2 permutation proof. And that's what you're going to see today. And it's very simple and very intuitive. So before we move forward, I just want to clarify that we are not the first one to achieve this asymptotic. There are these 2 very elegant work by Franzese et al. On CCS21 and by the Saint Guilhem et al. On SCN22. They are all very elegant, achieved as an asymptotic. However, what we actually improve here is that we improve the constants. Let me emphasize here, the improvement here comes from the smaller size of circuits, not implementation. It's just a smaller size of the circuits. So let's get into some technical details. Unfortunately, due to time limitations, I won't be able to present the full technical details here, but I want to show you how you can use one shuffle to make a read-only memory. Then we just want to support load gate, not store gate. And I'm going to give you some hints how you can upgrade this into a ZK RAM finally. So let's start with the permutation proof. So the permutation proof here I refer to is a very typical and classical one. Essentially, the task here is that you have 2 sets of wire, X and Y, they are of length N, and the proofer wants to prove to the verifier that X can be permuted to Y. So how can you do this? This is a very simple task. The very key observation here is that if X can permute to Y, you can induce these 2 polynomials Px and Qx defined as follows. And if X can permute to Y, if and only if this polynomial P is equal to polynomial Q. So what you can do is you just ask a verifier to issue a random evaluation point alpha and ask a proofer to prove that P evaluated alpha is equal to Q evaluated alpha. And the sound is coming from the Schwarzschild-Damilo-Lipton lemma. So note that this construction is very, very efficient. You only need 2n-2 multiplication gate to basically calculate this 2 product. And one thing I want to mention here is that this tree can be generalized into the vector of tuples rather than just a single dimension of tuple. That means that this vector, each element can be viewed as a vector. Okay, so let's finish this basically finished the permutation proof. Now let me show you how you can use just one permutation proof to build a read-only memory. Let's recall. So the goal here is that we want to build this load gate. Essentially, when we take some index I, we want to fetch out whatever safe in index I. And for simplicity, let's try to build a zero-knowledge RAM for the table I put here. We have only 3 elements which save x0, x1, and x2. And for simplicity, let's even imagine this table is public, known by the proofer and the verifier in clear text. I want to remark that our construction does not have these restrictions, but for simplicity and to understand our construction, this is already sufficient. So the very key insight here is that because proofer knows everything, there's no privacy for the proofer. So proofer can if we want to load the index I, we can ask a proofer to directly input xi. This should be good enough. However, of course, this only works for correctness argument because a malicious proofer can input arbitrary things. So we need some extra check to ensure that P does not cheat. So how can we do this? At a very high level and very informally, what we show here is that we can construct a one-time readable entries and create a reading history log using this permutation proof to ensure that proofer actually give me a correct value. So let me show an example. Let me show how this works by these examples. So essentially, this entry here I refer to going to maintain this triple with index value aversion. Here, aversion you can imagine as just what is the last time each unit being assessed, and every time when you assess it, you're going to increase it by 1. And I'm going to maintain these 2 arrays, one is called write and one is called read. However, note that this is just the naming of these 2 arrays and nothing to do with the load and store. So in the setup phase, we're going to put basically 0x00, 1x10, 2x02, 0 in this write array. It basically means that we have 3 very initial versions of these 3 units. And for each access, we're going to consume 1 unit in this write array and going to create a new versions into the write array for the future access. Let me give you examples. Let's say the very first load is one, we want to load the index 1. And for simplicity, let's imagine this one is just public. So what you're going to do is that you ask a proofer to give me what is the value inside the index 1, which is y0, and what is the latest version, what is the last time this array being written to this write array. You just put it down in the write array, and going to add one more entries, 1, y0, v0 plus 1, into the write array. So basically, you're going to consume the 0x1 1x10 entry, and you're going to create a new entry called 1x11. Similarly, you can load index 0. The next time when you load the index 1, the proof again going to provide some value and the latest versions. Notice that now, because the index 1 has been touched before, so the current version is 1, not 0 anymore. So you're going to write down 1 y2 v2, and you write back 1 y2 v2 plus 1 to the right array. And then finally, when you finish your access, we ask a proofer to perform a tear down phase. Essentially, here a proofer is allowed to basically tell us what is the latest version of each index. For example, here 0x0v3, meaning that the last time this x0 being accessed is the version v3, which should be 1 in this case. Similar for 1 and 2. So the crucial kind is the following. Finally, we're going to ask a proofer to permute a permutation proof to show that this read array can permute to write array. Or say differently, they are basically the same element in these two arrays. And the claim is, if this read can permute to write, the proof will never cheat. So let's see why. But before we do that, let me emphasize this is very efficient because it only costs you 2n plus 2t minus 2 multiplication gates to do this permutation check. So the observation here is very simple. Because if read can permute to write, it means that every index 1 in the read can also permute to every index in the write. So essentially, this means that every entry in the write array with index 1 can find an element in the read array and vice versa. So I want to remark that here, because we have 1 y0 v0 and we have 1 y0 v0 plus 1. So there's no way for you to cancel out these two elements because they just differ by 1 already for the last entry. Okay, so in the honest case, basically the proof are going to form this read history. And essentially because this 1, y0, v0 going to cancel out 1, x1, 0. It means y0 equal to x1. And similarly, y0 going to equal to y2 equal to x1. So it basically performs read correctly. So say differently, you can see this very simple picture. Basically, for each index, you're going to form basically a cycle. You start from x1, and finally you end up with x1. You may already notice there's an issue here. Namely, you can have another way to finish this proof. However, notice that even for this attack, the y0 and the y2 is still equal to x1. So this does not break the semantic of a read-only memory. So this picture basically shows that you can read from the future. However, because in the future you still write back x1 in the tear down phase, there's no way for you to break the soundness of this ROM. So actually, this is the main difference between the ROM and the RAM primitive. In the RAM primitive, we must prevent the proofer from reading from the future to break the soundness. And I'm not going to tell you how, but at a very high level, instead of using version, we can use this timestamp and ask a proofer to prove that the time difference is positive. Essentially, it reads from the past. But how can we prove it is positive? I'm going to leave you as a puzzle, and the hint here is that you can consider RAM with basically 1 to 2 indexes. And the most fascinating part here is that we have this paper you can check. You don't need to perform the zero-knowledge proof to prove to me that you find it. Okay, so this is very efficient. Finally, I just want to emphasize this is a very efficient constructions. For each access on amortized setting, we only need 2 inputs and 2 multiplication gates for every single access. And this finished the presentation for the ROM. And we implement this ROM using this VOLE-based zero-knowledge setting. And the real number actually reflect our asymptotic analysis. With this, thank you for your listening. And I'm happy to take any question you have.